Welcome back to CE 529. We are going to start talking about shockwaves a little bit. So this is sort of what we were discussing the last time. So one thing is, so we did one problem there where we try to find the max delay, and for a situation like this where vehicles were arriving. So it's kind of like a queuing theory. And what I also mentioned was that queuing theory is sort of focused on one point, so in space that will have a queue. So in this case, in the example that we did last time, it was about the gate of a national park. That was the idea there. Like, we were looking at the queues there, and this was so the diagram. You have number of vehicles on the y-axis, time on the x-axis. And you could do in a first in, first out type of queue, the largest vehicle delay, you just do. So you could, if you ever want to look at the delay, it's the horizontal difference between the departure curve and the arrival curve. So this is right here. If you look at this, this is your arrival curve. And then this is your departure curve right here. And you can see the departure curve always has a constant slope. It never changes, but the arrival curve does change here. So anytime you look at the vertical difference between these two curves, that's the number of vehicles. So that always gives you the size of the queue, because the vertical axis is number of vehicles. So anytime you're looking at this difference right here, gives you the size of the queue length or size of the queue in vehicles. And then if you look at the horizontal direction, it always gives you the delay, because the horizontal axis is time. So it gets you the difference between the departure time that I'm showing now minus the arrival time. And this whole line, it will represent the delay. And this delay you can represent, by the way, for any vehicle. These broken lines, this is the maximum delay, and this is the maximum queue length. Okay, maximum delay and maximum queue length. But if you were to draw this line somewhere else, let's say if you were to draw it here. So for example, they do it here, delay for the 100th vehicle. So you can do that. Like if you pull in a line from number of vehicles equal to 100, you can do that. If you want to find out delay for the 200th vehicle, you can just go here. And you can just go here and then measure this distance. You can measure this horizontal distance, and then that will give you the delay for. So, and then we know that 160th vehicle arrived just as the queue was maximum. So that's why they have the longest vehicle delay. Okay. So this is sort of like a graphical representation of the solution. So the homework problem that I have for you, so this week's homework will have two problems. One on that lane changing problem that we talked about earlier. Okay. And then this one as well. And the problem for this one would be, problem for queuing theory assignment would be, is this problem. And this problem is basically very similar to what we just did. The only difference in this problem, maybe let's give it a minute. Can you spot the difference between, I don't like the word. I've said this before, probably. I don't like the term accident. I like the term collision or crashes. Let's change that here. Okay. So why don't you give this problem a read for 2 minutes and tell me, you don't have to solve this problem. This is your homework problem, so you don't have to solve it right now. But can you tell me the key difference between this problem and the park ranger problem that we solved the last time, the queuing theory problem that we solved in the class on Tuesday? How is this problem different than this one? What's the key difference? Yeah, I'll take a pause here. So yeah, so the response I've gotten is from Blake is that the flow stays the same, the capacity changes. But if you want to talk it, and that's mostly correct in what you're trying to say, I would just use the terminology that we use in the queuing theory. So I would say that in this example, because nobody is sort of changing their routes. They all keep coming in at the same rate. So your constant flow, your arrival rate of 2,900 vehicles per hour is always the same. Okay. And your departure rate, though, it starts at 0. And then it changes with a partial open of the freeway. And then it comes to the full capacity. Okay. So that's the difference. Like, the problem. In that problem, the arrival rate changed and the departure rate was always constant. In this problem, your arrival rate is always constant and your departure rate is going to change. So want you to solve this problem for the homework. There will be additional one, as I said, on lane change. So there will be 2 problem homework. This is just one of them. And again, it will be due on Tuesday of next week. So you have about 5 days to do those 2 problems. Okay, so I'll let you work on this. Very similar to what we talked about last time. You just have to write those arrival departure equations. Any questions about this? Okay, so what I'll do is I will go on to the next topic, which is shockwave. And shockwaves are also about the Q formation and Q dissipation. But when you look at a Q from a shockwave perspective, it's not exactly, the Q is not abstracted to be at one location. The shockwave recognizes that the Q actually occupies the space on the roadway. So if there is a traffic queue, if you analyze the traffic queues using shockwave method, shockwave approach will always recognize that the queue is being taken, is taking up roadway space essentially. Okay, so that's the key difference. So what is shockwave? Shockwaves are essentially the boundaries between 2 different traffic states. Okay, and a lot of times those different traffic states are defined by a change in density. So shockwave is the boundary. One side of the boundary, you have higher density, and on the other side of the boundary, you have lower density. So that's what shockwave is. Shockwave is just a boundary. It's not a good or bad or anything like that, because there are both types of shockwaves. There are forming shockwaves, there are recovery shockwaves. So shockwaves by themselves may be a good or bad thing, but in traffic terms, all they do is define the boundary between 2 different densities. Okay, on one side of the boundary, you'll have higher density, one side would have lower density, and then that boundary itself would be moving, and that's what the shockwave is. Okay, so shockwave occurs in traffic stream during transition between 2 traffic states. Forming shockwaves means as the boundary is moving, it's bringing with it higher density, means more congestion. Okay, so that's your forming shockwave. It's transitioning to higher density. And recovering shockwaves, which is transitioning to lower density. Okay, shockwave speed is just the speed at which that boundary moves. Okay, and the most common cause for shockwaves is if there is a change in capacity. If there is a change in capacity. Now, that's not to say that shockwave can never form without change in capacity. They could. It doesn't always have to be a bottleneck necessarily on a freeway to cause a shockwave. There could be any different reason. In fact, they did an experiment in Japan where they asked drivers, without cruise control though, they asked drivers to drive at a constant speed of whatever, 20 miles, 30 miles an hour in a circle. But it's hard for drivers to maintain that speed without the cruise control. And even in that scenario where there was no reduction in capacity or anything, they had a bunch of drivers just driving around, and there were shockwaves that were forming even on that circular route. So there could be many reasons for shockwave. And this is sort of an interesting place for you to sort of go and check out simulation of shockwaves. So this is something I'll let you all play with, but I just wanted to demonstrate this. So if you pump up this on-ramp flow, maybe I'll just reduce this inflow a little bit. and I'll increase the on-ramp flow to be quite high. Okay, so I reduce the inflow. Inflow is the inflow from here. So I just now see it's reduced to like 1080 now. But I bumped up the on-ramp flow to be like 2000. Okay. So right now, the inflow from this location is too small to cause any kind of shock wave going backward because the flow is too small and there is no reduction in speed is necessary. But if I kind of keep increasing this inflow now a little bit, if I increase this inflow a little bit now, now what you'll see is this bottleneck for on-ramp vehicles starts to cause some sort of a shock wave. I can't. I want to reduce the time lapse a little bit. Okay, what I want to show you is that right now the boundary between the high density and low density is over here, right? On this curve. Okay, now it's going to go a little bit faster. So note that the boundary is here right now, and I'll reduce that. And then when you go and time lapse it a little bit further, you can see that that boundary now is shifted here. And these boundaries keep moving back and keep moving back and keep moving back. You see, what is going on is this boundary between low and high density that used to be over here, now it's shifted all the way back here. So that is what the Shockwave speed is that what is the difference? How fast is that boundary moving between the uncongested regime and the congested regime? Okay, so that's one thing that you want to. And then again, there could be like local shock waves as well. So you could see that there is high density, and then there is a little bit of a low density, and then there is high density again. So there might be some of that goes on as well. But the idea is we always look at the boundary of the density regime changes. So wherever that regime changes, how fast is that boundary moving is what we call the shock wave. And you can sort of play around with that and all that. This is a good portal for you to kind of play around and visualize different situations. I think they've done ramp metering. They've done all the other things as well. So if you want to have some fun with this website, the link is there on the slide. So you can visualize a lot of different traffic scenarios. And so they have this on-ramp scenario. They have the ramp traffic coming in from the other side. You can have like uphill climbing. I think this one's the uphill climbing. And you can pause it, you can refresh it. So now it kind of resets all these parameters back or starts the thing from zero. So everything's kind of going back to zero. I don't know if there was a signal that you could go to roundabout. But I'm more interested right now in this situation that is talking to me, that I'm discussing here, because I'm interested in that freeway bottleneck. So I definitely check this out, but I just wanted to give you a visualization of how that boundary moves. So next thing I want to talk about is how do I derive the speed of this boundary? In fact, if you know that there is a way to, actually figure out how fast this shock wave actually moves, there is actually a formula for you to be able to do that. You can figure it out. Let's try to see if we can derive that formula for ourselves. And let's say this is your bottleneck, and on this side of the roadway, on this side of the boundary of the shock wave, so this red line, let's say, represent one snapshot of that shock wave movement. Okay, just one picture of where that shock wave is right that second. You want to figure out the speed of this shock wave, this red line, and that red line is separating two different traffic regimes or traffic states. First regime has a density of K1 and speed of U1. Okay, the second regime has a speed of U2 and density of K2. Okay, and those are the two regimes being separated by the traffic, by the shockwave. And let's assume that your shockwave is moving at a speed UW. Okay, so this UW is the speed of the shockwave, and let's assume that it's moving with traffic. Okay, so I'm assuming that this W shockwave is moving at a speed UW with the traffic. Where the traffic is moving to the right. Okay, traffic is going this way. Okay, and my shockwave is moving in the same direction. Okay, and this is just a snapshot of that traffic. Okay, now can you tell me what is the relative stream or relative speed? What is the relative speed of this traffic regime if you were sitting on the shockwave? Okay, so now think of yourself as somebody who is moving with the shockwave. You are moving at a speed UW. Okay, relative to you, if you're moving at a speed UW, can you tell me what do you think to you the speed of this this traffic state would be? At what average speed would the vehicles that are actually moving at U1 would be moving relative to you who is sitting on a shockwave? Looking at speed though. U is a speed. U itself is a speed. So U1, UW, and U2, they're all three are speed values. The idea of relative speed, I want you to think about. It's kind of the theory where, you know, if you are in a moving source, something that is moving at a certain speed won't appear for you to be moving at the same speed. It will be actually moving at a different speed if you are moving with the source, if you're in a moving source. So what I'm asking you to imagine is that you are actually moving at the speed of the shockwave, UW.
Are we assuming UW for U1?
No, UW is not equal to U1. I'm saying U1 is the speed of the traffic speed on one side of the shockwave. U2 is the speed on the other side of the shockwave. And the boundary itself would be moving. Okay, yes. That's exactly right. So if you're moving with traffic, if I'm assuming all of these are moving with traffic, and if you are moving at if this traffic is moving at U1, you are moving at UW. So to you sitting on this shockwave, you will think that this traffic speed is moving at U1 minus UW. The relative speed that will appear to you would be U1 minus UW. Okay? And similarly, and that will be the speed that you will think that these folks are moving. Same idea, you can figure out at the speed which these state 2 folks would be moving. Okay, so this is a very, like, it's the same idea. Like, you know, if you're moving at UW, somebody who's actually moving at U1 would appear to you as if they are moving at U1 minus UW. And if you're moving against the traffic, it's the same idea. The car that's approaching you, it's approaching to you. If you're moving in a car and then a car is approaching you, the 2 cars are moving closer at a speed U1 plus U2. Like if you have opposite moving cars, because, you know, their speed gets added up because they're closing in at that speed. So it's the same idea. If they're all moving in the same direction, you subtract the speed of the source where you are observing the data from. Yes.
I'm just not sure what U1 to W. So is U1 before the shockwave? Like
not I wouldn't call it before necessarily. I would just call it like one side of the shockwave. The traffic is moving. So if you go back to this, diagram right here. I'll go back to this diagram right here, right? So I showed you, so I'm going to make it increase the on-ramp flow, get rid of all the traffic. Okay. And now if I go real high. I want to get it back to. So what I'm saying is, oh, it's time lapse, lower speed. So what I'm saying is the U1 is the speed of traffic over here on this side, and U2 is the speed of traffic over here. So it's like the boundary is this one, and one side of the boundary, the traffic speed is U1. The other side of the boundary, the traffic speed is U2. And we're talking average space mean speed of traffic. On average speed as the cars are moving at. Did I make it clear? What U1 and U2 are? U1 is the speed over here, U2 is over here, and you're assuming that you are moving with this shock wave. And this shock wave is moving backwards, but that's okay. We can make an assumption that it's moving with traffic for now, and then our answer will come out negative.
Okay, so this diagram is like looking backwards.
So
Like it's
the
like
diagram
looking-
that I'm looking at here, okay.
Like this is like relative to how the shock wave is traveling, not which is opposite.
Yeah, so this is all like all in the movement of shock wave. So all the traffic is moving this way. So the traffic is moving this way. My traffic is all moving this way. And this traffic is moving at speed U1. This traffic is moving at U2. And I don't know which is higher speed, which is lower speed. I'm just going to assume that everything is moving this way. And my UW is the speed of the shock wave. And that's also moving in the same direction. That's my initial assumption anyway. And if that assumption is wrong, I just get my answer to be negative at the end. And that way I'll know that actually the shock wave is moving against the traffic. It's moving in the opposite direction compared to the traffic. But this does let me know that I can figure out the relative speed. Now, this relative speed is important because if I know the speed of the traffic stream, and I know the density of the traffic stream, what can you do? Speed with density, can you derive the flow of the traffic stream? If you know the speed of this traffic stream, and if you know the density of the traffic stream, can you derive the flow? What would that flow be? Speed times density is exactly right. So speed time density would be your flow. So that's easy enough. So we know the relative speed of this one. So I'm going to type some things here. So the relative speed of this one was U1 minus UW. Okay, so that's my speed. We know the density on this side is K1. So if I do K1 times U1 minus UW, that will give me any point on this state one, how many vehicles per hour when I'm on the shock wave, when I'm moving with the shock wave, okay? When I'm moving with the shock wave, this is the flow rate that I will observe. Okay, okay. Now, if I want to see how many vehicles are going to pass a point, and let's say in time t, I can figure out that in time t, I'm going to watch K1 times U1 minus UW times t vehicles pass any point on this traffic state one. And I could actually do the same exact thing for state two, because the state two vehicles are, at least relative to me on the shock wave, they're moving at U2 minus UW. I can multiply that with density to figure out the flow rate, which is K2. Okay, K2 times U2 minus UW. And then if I multiply the flow rate with time t, I can figure out the number of vehicles that at any point in that state will be moving, will be passing at any point on that traffic regime. Okay, so because I'm on the shock wave and I know that this is the number of vehicles passing me based on the traffic state one, and this is the number of vehicles passing me based on the traffic state two, what has to be the relationship between these two numbers? What has to be the relationship between number of vehicles passing me based on the conditions of traffic regime one, and number of vehicles passing me based on the traffic regime T2, and You have to assume that I'm on that boundary of the shock wave. Can you think of a relationship between these two numbers? K1 might be greater than K2, but I'm looking at the number of vehicles that pass me on either side of the boundary. Yes. Yeah, it is a conservation of flow. That's exactly what it is. Essentially, you're measuring the same vehicle, right? You're measuring the same number of vehicles. You're measuring one from based on the flow rate or the density conditions of one side, and the other one you're measuring from the density of the other side. But basically, what this is measuring is how many vehicles are now crossing over this boundary. This calculation is based on traffic state 1. This calculation is based on traffic state 2, but they are measuring the same thing. How many vehicles are passing that shockwave boundary at any given time? So what has to be the relationship between these two numbers? These two numbers have to be exactly the same. These two numbers have to be exactly the same because that's what you're doing. You're conserving the flow. Yes.
That's not necessarily when the vehicle is passing at time t.
Yeah, so time t is no, it's like t is like a interval of time.
Yeah, so
It could be 30 minutes, it could be 1 hour.
But it's not like number of vehicles passing at
Yeah, no.
vehicles having passed in that.
Oh, that's a great question. So yeah, that's exactly right. So t is actually, so the question is this t an interval or is this t at a given time t? So here t represents any time interval. So it could be 30 minutes, it could be 1 minute, it could be 5 minutes, it could be 1 hour, whatever it is. So t represents any time interval and not a point in time. Okay, because what you're doing is your vehicles per hour is your flow rate. So if you take only this part of the equation, if you only take this piece of the equation, okay, this piece of the equation is a flow rate, and you multiply that by an interval of time, then you get the number of vehicles, and that's what you're trying to get. And you're doing the same thing here. So t represents a time interval. Now, if that is the case, if you equate the two equations, if you say, okay, that's wonderful because I got K1 times U1 minus UW equal to K2 times U2 minus UW. And I'm assuming that I had the same interval of time, so I canceled it. There is no t here because I canceled the t because I'm talking about the same time interval. So now if you simplify it, if you try to solve UW, can you do that for me in next 1 minute or so? Can you derive the value for UW for me here? So equation for UW. So this is like a little bit of an algebra, but still should be doable. Okay, you all get the same thing, K2 U2 minus K1 U1 divided by K2 minus K1. That's what you all get. Okay, and now I know what K2 U2 is though, right? K2 times U2, what is that? Flow rate, right? It's flow rate of the regime 2, and then K1 is flow rate of regime 1. So I can simply say the speed of shockwave is easy to derive because I can simply say this UW is equal to Q2 minus Q1 divided by K2 minus K1. Probably should put in parentheses here. So anytime you know the flow rate and densities of the two regimes that are being separated by a shock wave, you can derive the speed of the shock wave. And you can also see that if the flow rate is the same, and then this will have the units of speed, by the way, because this is a speed difference in flow rate, This is difference in density. Take the ratio, you get the speed units. Okay, so that's also good that that is consistent with that. So you can derive speed of a shock wave using this. So that's another little thing here that we could do. And let's see. Okay, so the Shockwave and queuing theory, they're both sort of important techniques of traffic analysis, particularly for modeling freeway congestion. Both analysis techniques are deterministic, and both are related with this fundamental relationship, which is Q at a given X and T equal to V times X and T and K times X and T. And where X and T are not multiplication, but they're like, you're representing density as a function of X and T. V speed as a function of location X and time T. Density at location X and time T. Okay. So now the definition of T is a little bit different than it used to be in the previous slide. Okay. So now we're talking specifically at time T. Okay. So here's the problem I want to work on. So if you give me a minute, I'll stop sharing. Okay, so this is the problem I want to work on next, is that I have a freeway segment, and this is it's an old TRB paper. It's a classic 2001 paper that was published in the Transportation Research Board Journal, and it was presented at TRB annual meeting in Washington, DC. Very interesting paper, and it was from Canada, so they're using kilometers and stuff, which is fine. So you have a 10-kilometer segment of the road. Okay. So let's assume that the first point of the road is x naught equal to 0. The last point of the road is x3 equal to 10 kilometers. What I'm going to do is actually draw it out. Okay. And it's subdivided into 3 10/3 of kilometer segments, x0 to x1, x1 to x2, and x2 to x3. A freeway flow, x0 t, enters the section x0, and then there is a ramp that feeds in always 400 vehicles per hour at x3 without delay. Okay, ramp flow is not very large, so ramp has the priority. So ramp can always feed in that 400 vehicles per hour. Ramp vehicles never wait. So this is like a simplifying assumption, but we'll go with this for now. Okay. And each of the 3 segments has 2 lanes with a combined capacity of 4,000 vehicles per hour. And then the flow density is shown in figure 1. The downstream segment x3 to x4. So once you pass x3, has only a capacity of 3,200 vehicles per hour. Okay. So this is what your flow looks like. So what I want to do is I want to draw this out a little bit. So let's see if I can stop sharing this, but share. Draw this out a little bit. So, we might not be able to solve the full problem today, and that's okay, because that's our next homework problem anyway. So let's think about this. This is my freeway. So let's say this is my freeway. I'm going to start drawing here on this side. And this is my freeway here. Okay. And then it has 2 lanes. Okay, so it has 2 lanes. Oops, lane marking is sort of off, but that's okay. We have 2 lanes of the freeway. And my first point here is X0. And then at 1/3 of the distance, I have point X1. At 2/3 of the distance, I have point X2. And then this last point is X3. And something interesting happened after this. For some reason, the lanes are narrow or whatever it might be. I have some sort of a bottleneck beyond this point. So beyond this point, my freeway looks something like this. Some sort of reduction in width or whatever it is. It still has 2 lanes, but the width is somehow reduced. And my X4 segment is my X3 to X4 segment. So what is going on here in this problem is that I have a 4,000 vehicles per hour capacity starting here and all the way up to here. Okay. But beyond this point, beyond the point X3, beyond this point right here, my capacity drops to 3,200. My capacity is only 3,200 here, but it's 4,000 over here. So, and then there is a ramp here. And I'm going to move it on the left just because that's where I have the. So there is a ramp here that always feeds in 400 vehicles per hour. A ramp here that always feeds in 400 vehicles per hour. Is the parameters of the freeway a little bit clearer? Like, clear what is happening in the freeway. So always, just remember this. What's that? No, ramp is at X3. So there is a 4,000 vehicles that come in from, 4,000 is the capacity. There is a demand that freeway flow comes in at X0. But the ramp is at X3. At a constant flow of ramp, QR equal to 400 vehicles per hour enters at X3 without delay. So 4,000 is the capacity, 3,200 is the capacity here. But if you look at the next step in the problem, they give you some demand parameters. Give you some demand parameters now. The mainline demand is provided below. So the mainline demand is 3,200. So the mainline demand that comes in, this 4,000, 3,200 vehicles per hour is the demand that comes in at X0. Okay. So please remember this, 4,000 is the capacity. So I'm going to highlight this over here. Highlight this over here. And make sure I'll share this capacity. Okay, so capacity 4,000, but the demand, and then this is the capacity at X3. So some kind of a bottleneck is there, and the capacity reduces to 3,200 beyond this point. And then your mainline demand itself is 3,200 vehicles per hour for the first 15 minutes. And then it reduces to 2,000 vehicles per hour otherwise. So after 15 minutes, it goes down to 2,000 vehicles per hour. Now, so this is sort of the parameters of the problem. And one thing I want to say is that first, let's think about where might the queue fall. What would be the origin of the queue at this location? What would be the origin of the queue at this location? Yes, it'll be X3, right? Because if you have 3,200 vehicles per hour coming in, then the capacity is 4,000. So pretty much there would not be any queue because everybody can just depart at the speed that they want to depart at. Okay. So they can just leave. They can keep going, keep going, keep going. When this 3200 demand reaches right at this point, why would there be a queue? Why would there be a queue at X3? Yes. Yeah, the demand is 3200 from here, from the main line. And then 400 vehicles get flowed in from here. So now you'll start to see, okay, 3600 want to pass through, but only how many can go through? 3200, right? So that arrival rate and departure rate difference, so your arrival rate will be 3600 at X3, but your departure rate is only going to be 3200 at X3. That's going to create a queue rate or queue formation rate of about difference of 400 vehicles per hour. So that's what's going to start accumulating at X3. Make sense? Right? So that's good. Now, if I were to ask you what time, let's say the traffic is moving is, let me just give you, the traffic is moving at 100 kilometers per hour. Let's assume that the traffic moves at 100 kilometers per hour, and this is a 10-kilometer segment, and traffic is moving at 100 kilometers per hour. Can you tell me at what point in time would the queue start to form? Assuming that the demand starts here at t equal to 0, it becomes 3200. The RAM demand is 400 from here. At what time would the queue start to form at X3? At point X3. The traffic moves at 100 kilometers per hour. Six minutes is right, because if you're moving at 100 kilometers an hour, if the traffic is moving at 100 kilometers an hour, then it takes 6 minutes to travel 10 kilometers, right? 100 kilometers in 60 minutes, so 10 kilometers in 6 minutes. So until, and remember, there would be no queue before that, because these 400 can always pass through, because this 400 is way lower than 3200. So they can always get by. Only when this 3200 demand from here meets the 400 demand from the RAM, that's when the problem starts to occur. So your queue will start, if traffic is moving at 100 kilometers an hour, then the queue will form at X3 at t equal to 6. Can you analyze that queue using an input-output diagram? And now the question would be, can we solve this problem using the input-output problem as an input-output problem? Okay. So the initial, what's the initial departure rate? What is the initial departure rate here? So let's write down some arrival rates and departure rate. Don't worry about this homework problem yet. So let's talk about what is the arrival rate at X3. So I'm only talking about X3 here. What is the arrival rate at X3? Yes. No, arrival rate. Right? Rate always I want to measure in vehicles per hour or vehicles per minute. How many vehicles are arriving? So arrival rate, when I say arrival rate, I'm talking about simply the queuing theory problem. I'm trying to set this problem up as a queuing theory problem, just what we learned last Tuesday or this past Tuesday. What is the arrival rate here at X3? 3200 is the departure rate, though. That's the capacity, right? So 3200 is what you can depart from X3. So the departure rate, actually, you're right. Departure rate at X3 is 3200 vehicles per hour. And I can convert that into 3200 divided by 60. That's about 53.33, I guess. 52.67 vehicles per minute. Does that make sense? 3.36. Okay, so that's your departure rate at X3. But I still haven't gotten the answer for arrival rate at X3, because capacity will always determine the departure rate, right? Capacity will only determine the departure rate. It won't determine the arrival rate. Arrival rate would be, whatever it is. So tell me what it is. 60 vehicles per minute is the right answer, actually, because it's 3,200 demand from here, from the bottom. 400 gets added from the ramp. So your arrival rate is 3,600 vehicles per hour. And then that's basically 60 vehicles per minute. Okay, now, so this is, and then is this arrival rate always constant? No, right? It's not constant. And remember, I'm analyzing at t equal to 6. So I'm going to assume at t equal to 6, this is what happens. Okay, this is what happens at t equal to 6. So this arrival rate changes to what? This arrival rate changes to what according to our problem? If you look at here, if you look at this number, that the Q from the bottom reduces to 2,000 vehicles per hour at t equal to 15. So 15 minutes later, what happens to the demand? It reduces to 40 vehicles per minute. Why 40? Because 2,000 from the bottom, from X0, and then 400 get added at the ramp. So demand reduces to 2,400 vehicles per hour after t equal to 60 minutes. So at t equal to, and I'm going to say that this is all happening 6 minutes delay. So when the demand reduces here, let's assume that all of that reduces here at t equal to, it's all going to happen at t equal to 15 minute or 6 minute delay, because vehicles will take, if they're moving at 100 kilometers an hour, they'll reach here in 15 minutes. That new flow will reach here at 15 minutes. So I'm going to say this is between 6 t 21 and then 2,400 vehicles per hour, 40 vehicles per minute. And then this reduction happens at t greater than 20. I think you should be able to solve this problem. You should be able to solve this problem when this Q will dissipate, using the example that we did in the class. Because you have just change in arrival rate, and the departure rate is 53.33. With this departure rate at t equal to 21, the Q will start shrinking. Okay, and then when the Q shrink, it go away at a certain point. So you should be able to tell me when would the Q go away in this problem, right? Okay, so I'm going to stop here. We'll pick up this discussion in the next class. I'll also share this this file with you, so you have that. But we'll start talking about this problem on Tuesday. So we'll pick up this discussion from here. Oh, there is an ITE meeting today, so please feel free to check that out.